So, good morning guys. So, our topic for today is all about simple strain. So, simple strain, also known as unit deformation. Strain is the ratio of the change in length caused by the applied force to the original length. So, strain is a geometric quantity that measures the deformation of a body. Under simple strain, we have two types of strain. First is the normal strain, which is dimensional changes, and next is the shear strain, which changes in angles. So for the formula under simple strain, so epsilon is equivalent to sigma divided by the length, where sigma is the deformation and L is the original length, thus epsilon is the deformation. For the stress strain diagram, so suppose that a metal specimen be placed in tension compression testing machine. As the actual load is gradually increased in increments, the total elongation over the gauge length is measured at each increment of the load, and this is continued until failure of the specimen takes place. Knowing the original cross-sectional area and length of the specimen, the normal stress and the strain can be obtained. So the graph of these quantities with the stress along the y-axis and the strain along the x-axis is called the stress-strain diagram. So here is the example of a stress-strain diagram for a medium carbon structural steel. So the stress-strain diagram differs in form for various materials. So ibig sabihin niya, nag-iiba siya every type of material. Metallic engineering materials are classified as either ductile or brittle materials. A ductile material is one having relatively large tensile strains up to the point of fracture like structural steel and aluminum. Whereas brittle materials has a relatively small strain up to the point of rupture like cast iron and concrete. An arbitrary strain of 0.05 mm per millimeter is frequently taken as the dividing line between these two classes. So as you can see in the stress-strain diagram, so from the origin 0 to the point called proportional limit, which is the P, the stress strain curve is a straight line. So this linear relation between elongation and the actual force causing was first noticed by Sir Robert Hooke in 1678 and is called Hooke's law. So that within the proportional limit, the stress is directly proportional to the strain. So as you can see in the figure, proportional yung ating stress and strain. So ito yon, yung straight line. Then next, so the constant of proportionality K is called the modulus of elasticity or Young's modulus and is equivalent to the slope of the stress-strain diagram from 0 to P. Then for the formula, so stress is equivalent to modulus of elasticity times the deformation or epsilon. So usually, modulus of elasticity of steel is equivalent to 200 gigapascal. So, ayan, pa-take note. Then next, so dito tayo, balik ulit tayo. Then next is the elastic limit. So, ito yung elastic limit natin. So, ayan, elastic limit. The elastic limit is the limit beyond which the material will no longer go back to its original shape. So, ibig sabihin, hindi na daw babalik yung ating material sa kanyang original shape kapag na-applyan na siya ng force. When the load is removed or it is the maximum stress that may develop such that there is no permanent or residual deformation when the load is entirely removed. So then next, elastic and plastic ranges. So the region is in stress-strain diagram from 0 to P is called the elastic range. The region from P to R is called the plastic range. So, P to R is called the plastic range. Ito yun. P, so as you can see in the figure, ito yung P, then R. So, yun daw yung ating plastic range. Then, for the yield point. Yield point is the point at which the material will have an appreciable elongation or yielding without any increase in load. So, saan ba yield point natin? So, ito. So, ito yung ating yield point after the elastic limit. Then next, ultimate strength. So the maximum ordinate in the stress strain diagram is the ultimate strength or tensile strength. So ibig sabihin, kapag dumagpas na siya sa ultimate strength, so there is a huge chance na mag-fail na yung ating material. Then for the rupture strength is the strength of the material at rupture. So this is also known as the breaking strength or the breaking point of the material. So for the modulus of resilience, so is the work done. So break tayo sa ano. Modulus of resilience is the work done. So na yan, work done on a unit volume of material as the force is gradually increased from 0 to P in newton per meter divided by cubic meters. So this may be calculated as the area under the stress strain curve from origin 0 or O to up to the elastic limit E, the shaded area in the figure. So nasaan ba yung shaded area? So ito daw yan, yung ating shaded area. Shaded area in the figure. So the resilience of the material is its ability to absorb energy without creating a permanent distortion. Then modulus of toughness is the work done on a unit volume of a material as the force is gradually increased from 0 or point O up to point R. So this may be calculated as the area under the entire stress strain curve from O to R. The toughness of a material is its ability to absorb energy without causing it to break. And last, working stress, allowable stress, and factor of safety. Working stress is defined as the actual stress of a material under a given loading. So the maximum safe stress that a material can carry is termed as the allowable stress. So the allowable stress should be limited to values not exceeding the proportional limit. However, since the proportional limit is difficult to determine accurately, the allowable stress is taken as either the yield point or ultimate strength divided by a factor of safety. So the factor of safety is the discretion of the engineer, or it is based always based in different types of code. So the ratio of this strength to allowable strength is called the factor of safety. Then next, for the axial deformation in the linear portion of the stress strain diagram. So earlier we have defined that in the figure that stress is proportional to the strain. So ayun yung formula natin, di ba? So stress is equivalent to modulus of elasticity times the strain. Then next, since stress is equivalent to P over A, so di ba ang stress natin is equivalent to P divided by A, and then PA is equivalent to modulus of elasticity times strain times length. So after rearranging the equation, so ito yung makukuha nating formula where deformation is equivalent to PL divided by AE, where P is compression or tension force, then L is the length of the material, and A is the cross-sectional area of the material, and E is the modulus elasticity of the material. So to use this formula, the load must be axial. So axial, ibig sabihin point load yan. So we have different types of load. So uniformly distributed load, point load, ano ba? So varying load, and etc. So the bar must have a uniform cross-sectional area, and the stress must not exceed the proportional limit. So if however the cross-sectional area is not uniform, so kung hindi daw uniform yung ating material, the actual deformation can be determined by considering a differential length and applying integration. So ito na yung magiging formula natin if the material is not uniform in cross-section. Then next, where area is equivalent to Ty and Y in T if variable must be expressed in terms of X. Then next, for a rod of unit mass rho suspended vertically from one end, the total elongation due to its own weight is equivalent to rho times G L squared divided by 2E. So Next, so pag i-arrange natin yan, so mgl divided by 2e, where rho is in kilograms per cubic meter, which is also a density, and L is the length of the rod in and M is the total mass of the rod in kilogram, and A is the cross-sectional area of the rod in square millimeters, and G is equivalent to acceleration due to gravity, which is 9.81 meters per second squared. Then, stiffness, K, is the ratio of the steady force acting on elastic body to the resulting displacement. It has the unit of Newton per mm. And that's all for the basic principles and theories behind axial deformation. So, problem number 1 na.